when I put together this this PowerPoint, I just had on the title screen exam technique, the what, why, and how. And PowerPoint does this amusing thing where it makes suggestions about I don't know, design suggestions, right? Design suggestions. And one of the suggestions, or the suggestion it made actually, was this little short video in the background where it says something's out of focus and then something becomes clear. And I thought that was amazing that it suggested something so apt. So the other thing to say about it, the reason why it's apt is I think pretty much all of this has been in front of your eyes all the time. So yeah. Anyway, I'm amused. But there we go. All right, so let's get started. So we're going to look at the exam technique, the what, why, and how. So the first sort of half or part of this is going to be looking at my argument for what I think exam technique is and why I think what I'm saying is exam technique is exam technique, if that makes sense, and why it is. There's a sort of a general point to all of it, even if we can talk about sort of quite different individual examples. If you have any questions during the recording of this video, please put them in the chat box down below. Okay, let's get started. Right. Okay, so what am I saying exam technique is? Right. I'm going to put it in a nutshell. In a nutshell, I think it really boils down to two things. Obviously, I'm going to have to expand on these, but I think it really boils down to two things. Writing on your exam paper, and by that, I don't just simply mean the answer, because obviously that's obvious. So writing on your exam paper, and then doing this automatically, doing it habitually. So I've got to expand on that. I've got to expand on what I mean by writing on your exam paper. But fundamentally, that's what I think a lot of the exam technique that I think we're going to cover, they're all going to be like different examples with different questions. They all are writing on your exam paper. And the point about it being automatic and habitual, I'll come to later. All right, but that's it in a nutshell, I think. Okay. So to understand why what I'm going to say, why this writing on an exam paper is important or effective or is going to help or is exam technique, I think it's all about it's fundamentally about reducing the demands on your working memory. So we've got to understand a little bit more what we mean by working memory, but it's fundamentally about reducing the demands on your working memory. So what is working memory? Okay. No. So working memory is basically where you do your thinking, right? So when you're in an exam, when you're doing questions, when you're listening to me now, when you're reading what's on the screen, you're essentially using your working memory. I think this is a useful analogy. I'm sure there are some people who would argue that this isn't correct. This isn't a correct one. But anyway, I think a useful analogy is the differences in memory in your computer, if you have a computer. So you have RAM, right? So you have the random access memory, and you also have a hard drive. Okay, and basically the RAM is where, you know, when you open an application or you're performing a function on your computer, it's basically being done in the random access memory. And so if you have lots and lots of applications open, and that's when your computer starts to struggle. That's basically when the RAM is in effect overloaded, right? It's got too much to cope with. Your hard drive is where you store things in the long term, and which you would then access as and when you wanted to do a particular thing using your random access memory. And I think there's a similar way of thinking about, or the working memory is similar to your random access memory in your computer. It's where you're performing your functions in the here and now. And basically, you've also got a long-term memory, which is what you draw on. So that might be where the applications are stored or where the files are stored or whatever, which you then draw on when you're needing to do the operations in the here and now. So your working memory is, where you're doing your current thinking. And there is loads and loads and loads and loads and loads of research about working memory. I'm not making this term up. So it's active. It's what's carrying out any sort of ongoing tasks. So basically, it's what you're using when you're doing an exam. So if we think about answering exam questions, so I'm going to a little sort of diagram illustration here. So here's the exam question. and you are going to have to solve it or answer it using your working memory. Now, to do that, you need to draw on your long-term memory, and in your long-term memory is your knowledge, if you like, the things that you have learned over time. Now, they can be stronger memories or weaker memories, and they could even be non-existent memories, in which case they're not a memory, are they? But the point is, to be able to answer a question, you do have to draw on knowledge, and so fundamentally, even when we talk about exam technique, whilst it can be helpful, whilst it can certainly make a difference, no matter what your knowledge is. I mean, fundamentally, it still is relying on what you've learned. So it's not a quick fix. It's just, how can we call it? I would probably refer to it more as marginal gains, right? So tweaking a bit here, getting an extra mark here, getting an extra mark there, getting an extra mark there, and cumulatively, it's like marginal gains. If you know about British cycling and the way that they transformed it, they talked about how it was all about marginal gains, a fraction of a second by changing the aerodynamics of a helmet here, fraction of a second by using a different chain or whatever it was, right? Different marginal gains, which ultimately transformed the British cycling team from being, I don't know, 4th place out of the medals to being, winning loads of gold medals. So, but what we can't do is we can't avoid the fact that you still need to know stuff, right? So that is the fundamental thing ultimately, is you need to know it. And what this exam technique is going to be is about marginal gains with respect to that. Anyway, you have your exam question, and you are now trying to work it out using your working memory, and so you draw from your long-term memory. So the more secure the knowledge, the relevant knowledge is in your long-term memory, obviously the more successful you're likely to be. There's no getting around that. If you needed, say, these 6 bits to be able to answer this exam question, if you're a bit shaky on one of them, it's going to be a little bit harder, but maybe it'll be okay. But obviously, the more shaky these are, or the more non-existent these are, then the harder and harder it becomes. So there's no way around the fact that you have to know stuff. And when we're talking about memory, it's not simply a recall of a fact. This is not, when we talk about long-term memory, I'm not simply talking about these atomistic pieces of knowledge. Oh, I know that thing, and I know that thing, right? There is an element of that, that's sure, that's true. And it's not simply about memorizing stuff. And the worst thing you can do at A-level chemistry is think that it's just a question of memorizing stuff. It's about that long-term memory is as much about how things are interconnected, right? How things are joined together. So it's not simply about a particular fact, but anyway, and it might be about a skill, okay, as well. It might also be about a skill. So I've just put knowledge there, but that could be knowledge of a skill, could be knowledge of a connection, it could be knowledge of a variety of things. Anyway, you bring that into your working memory, and then you use that to answer the question. Okay, that's sort of fundamentally, that's a sort of like a pictorial way of thinking about, what's happening in an exam situation, or when you're, to be honest, when you're answering any question, but we are focusing on exams here. All right. And my job as a teacher is to try and get the long-term memory stuff as secure as it possibly can be. Okay, that's sort of my job anyway. So what more about working memory? So the thing is, and again, there's lots and lots of research about it, you can only process a limited number of elements at a time. It does not have infinite capacity. It has limited capacity. There is nothing in the research to say that that long-term memory doesn't have infinite capacity. Of course, we've got to be a little bit careful by that, but there's nothing to suggest that your long-term memory is limited. But there is lots and lots of evidence about working memory. And this, is one of the reasons why phone numbers used to be presented in a particular way, because it chunked the numbers, and in a sense, it made it easier to sort of remember things, because you can only remember a limited number of elements, so you chunk them. So if it can only process a limited number of elements, then it has a limited capacity, and that means it can become overloaded. So like my analogy earlier with the RAM, just like you can have too many applications open at one time, your computer can struggle, it can go into the circle of death or whatever it's called, when the wheel just spins round and round on the screen. basically your ability to process and work through things can be hampered, severely hampered, if your working memory becomes overloaded. So part of what this argument is going to be about exam technique is about trying to avoid that as much as possible. So there's this idea of cognitive load, right? So just repeating what, in a sense, what I've said, your working memory can become overloaded, and that's what can make some exam questions more difficult than others. And obviously, there's an aspect of this. If we all have limited working capacity, and there's a various theories about whether it's 4 pieces of things or 7 pieces of things, and this is whatever it is, it's fairly consistent across people. But one thing to acknowledge is how well you know something in the first place. So that long-term memory stuff, how secure that stuff is in your long-term memory, how well you appreciate already how those different things connect with each other, those different bits of knowledge connect with each other, they are relevant to this. So one person can find one exam question much easier than, say, another person, simply because they happen to know it better. And it means there is less chance of their working memory being overloaded, right? So your working memory, one factor that affects your working memory, your ability to process a question, to answer a question, is fundamentally how well you know that topic and the information in the first place. Okay. However, there are things you can do to reduce the chance of overload, right? And that's really what this exam technique, I think is about. This is my argument anyway. This is my argument for why I'm saying what I'm saying. So how? So I've done the sort of what. So I think the issues are sometimes about the demands you place on your working memory. Those are the things that can make questions more difficult. Those are the reasons why you can make mistakes sometimes, silly mistakes sometimes as well, or you think of them as silly mistakes, but they probably happen fairly commonly. So you can call them silly, but if they're losing you marks, they're losing you marks. So this is what I'm trying to get at here. If what you're trying to do is, instead of burdening your working memory with all of the information it needs to hold on to be able to answer this question, my idea is that you're trying to reduce that load by placing as much of your thinking as you can on the page, on the exam paper. That's the fundamental point about writing on the exam paper. You're unburdening. You're not having to keep it in your head. It's now there in front of you to be used whenever you need to use it, whenever you want to use it. You've got to focus on the fact then that all of these things I'm saying are for your benefit. I mean, there's going to be the odd thing I say where you think, oh, I've been told that before. And you've probably thought when you've been told it before that it's always been about, I don't know, for the marker's benefit, for the person who's marking it, for their benefit. And there's no denying it would be to their benefit. But fundamentally, I want you to focus that what I'm suggesting is about you, not about anybody else. So if I'm saying writing as much of your thinking as you can on the exam paper, I am going to try and show examples, and like real examples, but I think it's about annotating the question, right? I think that's one of the things that's a big part of it. And there'll be different ways of annotating. There'll be different things that I'm going to be suggesting. So, and it may well be, to be able to do this annotation as successfully as you can, you are going to have to become more secure in some things. So again, it's, sometimes with technique, it's something you can practice or something you can get better at. So about annotating the question, chunking your answers. I'll explain that a little bit more, but it's you want to be trying to approach your answers as much as you can in steps, and to think about one step at a time and then go to the next step. And sometimes I fear that some of you just dive right in and are in the midst of everything in no time at all, and are just trying to do too much all at once. So chunking your answers. So how can we help you chunk your answers? Showing you working in full. This is the thing that I'm sure that you have had teachers tell you right across the years, right across the subjects, and you've probably gone, yeah, but this works for me. All I can say is the reason for showing you're working in full is to reduce the chance of making a mistake. It's basically to reduce the load on your working memory. You know, if you don't want to do it, you don't want to do it. But I think there's a very compelling argument for showing you're working in full, because you can see much more clearly where you've been, where you are, and probably then where you're going to go. And I think showing you're working full is an aspect of chunking your answers, to be honest. And very, very important. And so one of the things about this today is that it's not enough for me to tell you this stuff that I'm telling you today. It has to become ingrained. It has to become something you do systematically. It has to be something you would do automatically. What you cannot afford to do, or actually put it another way, it will not make any difference what I'm suggesting to you if you decide you're only going to try and do it in an exam, because it won't happen. It won't work. So I'm sure some of you have learned a musical instrument. I'm sure some of you have learned, I don't know, I've done some sort of, say, dance or something, or you've done sport and you've been coached, anything where you've been coached, right? You think about the classic extracurricular things where you get some form of coaching. You know, more specific coaching, one-to-one coaching, or, you know, one to a small group coaching. Whenever you're first learning that new dance move, or you're learning, I don't know, a new piece of music, or you're learning a new skill in a sport or something, you have to think about it when you're doing it, and it slows you down, and you're having to be very deliberate, and it's all very a bit ponderous, and then you keep practicing and you keep practicing, and then eventually you do it without thinking. Eventually, you're able to do whatever it was without thinking. In fact, another great example is tying your shoelace. When you first learned to tie your shoelace, it was just, you had to focus all your attention on it. You had to really struggle. You struggled, you got better, and eventually you just can do it like that. I wish my fingers could click a bit better than that. But anyway, like that. So, so the point is, again, these suggestions, if you feel that you want to employ them, you have to employ them from now. Okay, they have to be something that you automatically do. You cannot get there in an exam going, oh, what was it Mr. Flynn suggested about this sort of thing? Because what you're then doing is you're putting another thing on your working memory, another load onto your working memory, and so it's not going to be effective at all. I don't agree with that, Josh. But anyway, about them giving you no working space, but we'll come to that anyway. All right. Okay. So I'm expanding a little bit now on about what I mean by writing on your paper, and then fundamentally you've got to do it automatically, systematically, automatically. So there are things that you may need to practice and things that you need to do continuously from now on, if that's what you want to do. So I'm going to try and use an example type of question to sort of, this is not writing, this is more about using the ideas, the principles, trying to show the principles again. So mass spectrometry calculations, those sort of 5-6 mark questions. So basically what happens is, by the time we get to this point, there'll be some people that have no problem with them, they're absolutely fine with them. And then there'll be some people who'll go, I just can't do them. I just can't do them. And the thing is, you know, how long has it been now? 18 months since you first did them. And we're in a position where quite possibly some of you are just like, I can't do them. I can't do them. And that's not that I don't for 1 minute say that that is not true. But what I think is, well, why isn't this being fixed yet? Right? Why haven't you fixed it? Why hasn't there been some thought about sorting this out? So if we think about a mass spectrometry question, and let me just say, there's been one in every single exam paper, every single set of exams, both AS and A level. So these are like marks that you're going to expect to come up, to be honest, and therefore you need to, and you want to get them. So you get your exam question, and here's our working memory thing again. Now, I'm not saying this is exhaustive, but let's think now about the sort of things that you need to be strong at, competent with, and these are skills in this respect with regards to a mass spectrometry calculation question, because they do give you the equations by and large, right? So in fact, they always give you the kinetic energy equation, and they sometimes give you the velocity equals distance over time 1. So, you know, I think you need to be good at rearranging equations to do these successfully. I think you need to be capable of simplifying equations. I think you need to be able to convert units. I think you need to recognize what the correct units should be. I think you need to be able to use a calculator well, and we'll come, you know, that might be a bit of a surprise, but anyway, that's something. And then quite often they often have significant figure. Often is a mark, the correct number of significant figures, and so about correct number of significant figures. What I would say is I doubt very much that any of you have a problem with fundamentally understanding significant figures, but it is about applying them in the moment, and we'll talk about that. So how could we approach a question like this? How could we chunk it, right, when we're approaching something like this? Now, I have said, I'm sure maybe I haven't said very much to you lot, but I've definitely said to classes over the years, when, you know, they've found either this type of question difficult or certain equilibria questions difficult, or even things like buffers, okay? One of the things that students sometimes do is they just stick numbers in and then try to sort stuff out. I think you have to chunk it, right? You have to break it down into parts. And the very first thing for a question like this is get the equation ready for the numbers, all right? Get the equation ready for the numbers. So you need to be confident and comfortable with rearranging equations. Now, that might be something you have a weakness at the moment, right? Maybe rearranging equations is one of the big problems. So you see, if that long-term memory stuff isn't secure, then that's where the problems can arise. And then, so, you know, this chunking is only going to make things easier. It doesn't make things easy, okay? So, but, you know, that's something you should probably know. You should be aware whether you are confident or not at rearranging equations. And if you're not, then that's something you need to practice, okay? And that can be done. And the same with simplifying equations. So you get everything ready for the numbers, but you don't look at numbers at the start. You get everything ready for the numbers. Then you focus on the numbers. You think about, okay, is everything in the correct units? Do I need to convert any units? Admittedly, there's probably a little bit of pre-calculation, but, you know, just getting the units ready. So you might have about the mass of an ion or something like that. Get everything ready. Then once you've got all the numbers and you've got your equation ready to be used, then you've got to be able to use your calculator properly. And it would be easier to talk to you a bit about this live, actually. I mean, like physically in front of you, because one of the things I think you really should, if you don't already, something that you should get very strong at is using the fraction button on your calculator, because I think, and again, you know, so you have to develop a skill, but I think if you can write your expression out on your calculator exactly how it looks on the page, and you will have done it, you know, with the fractions and so on, then that is going to make probably you getting the correct answer more likely. And then ultimately you may have to give it to correct significant figures, and we'll look a bit more about that later. But if you're in the habit of doing correct significant figures anyway, then you are less likely to forget when it asks you to do it. All right. If you sort of go into an automatic mode of, I'm going to put all my answers whenever I do them to the correct number of significant figures. And if you're not sure about what the correct significant figure should be when you're looking at a question, then again, that's something that you can ask for help. I mean, you can talk to me and everything, but you need to be, you need to be aware of if that's a problem. And then once you're aware of it, then we can begin to do something about it. And then through all of that, hopefully you then arrive at the answer. Okay, so we're just trying to sort of break down. So the reason for this picture is it's not a magic, you know, this is what you need, you know, this is simply how you're going to answer it. It's just to make you appreciate how this combination of long-term memory, working memory can work together, fit together to arrive at an answer in an exam question. And so any parts of this are, the long-term memory is the fundamental bit. If any or many of these are shaky, then there's a significant problem. But even then, if you just want to make things as easy as possible or easier, then think about how you should approach questions. Okay, think about steps, think about chunks, think about this is how you would lay out your working, in effect, right? You would be doing these things bit by bit. Okay, where are we? It's a lot of me talking, isn't it? Showing your working in full. So every shortcut you take, and that's what you're doing when you don't show your working in full, I feel. Every shortcut you take increases the risk of your losing marks. That doesn't mean you will lose marks. Okay, risk is a thing. You know, and I'm hoping with COVID, actually, people are understanding risk a little bit better than they used to. Risk isn't something will definitely happen. Risk is about how likely it is to happen. To give you a different type of analogy, I really should have looked this up, but I will look it up for the more like proper video that I eventually do. But the chance of you being hit by a car if you cross the road with, I don't know, more than 10, you know, not at the pedestrian crossing, but maybe just a bit away from the pedestrian crossing, is way higher than if you cross at the pedestrian crossing. You basically are increasing your risk of being hit by a car by not going across a pedestrian crossing, but going anywhere close or distant from a pedestrian crossing. Now, so it's all about, therefore, risk of losing marks. Doesn't mean you will lose marks by taking a shortcut, but you risk it. If you, in a lot of the calculation questions, if you put the final answer and you only put the final answer and it was correct, in most of the marks schemes, they will just say award full marks, right? Great. But let's say your final answer is wrong. And if that's all you've done, or you've just jumped steps or whatever it is, you will not get any marks. Whereas it could have been that you just made a tiny mistake somewhere. And if you'd laid out your working in full, for his first thing, you'd probably be less likely to have made that tiny mistake. That's the first point. And the second point is, well, you might not have got full marks, but you might have got half the marks, or most of the marks, or some of the marks. Anyone who's aspiring for an A star, I always say, it's not about how many marks you get when it comes to A stars. It's about how many marks you lose. You can't really afford to lose very many marks, is really what it boils down to. Now, we're all going to lose marks. None of us are perfect. You know, everyone makes mistakes. That's going to happen. But let's reduce the risk of silly mistakes, basically. Okay. Systematically and automatically. So I hope I've sort of explained that. But it's about, you've got to form these habits now, really. If you feel that what I'm saying today is compelling, if you feel that what I'm saying is convincing, if you want to enact what I'm saying, then you need to be doing it every time you do any work from now on. You need to be practicing it. You need to be forming the habit. It needs to become automatic. Okay, it needs to become automatic. Because what you can't afford to do is start being there in the exam going, oh, yeah, he said something about this, or we said something about that, or what should I do, or what would make this? And the moment is, you're not thinking about the question anymore. You're not thinking about answering the question anymore. Not really. So like I said before about sport, music, dance, whatever, you know it. It's when it's automatic. That's when you're fluent in it. That's when it makes the difference. Okay, so now we're going to look at some examples. So let's, fingers crossed I don't make any mistakes. This would be quite funny if I did, wouldn't it? So this is not an exhaustive list of questions, and I would say that, you know, some of them, the writing on the exam paper has greater benefit for some than others, maybe, but it's just to sort of illustrate some points, I guess, maybe to begin to illustrate both metaphorically and literally, actually, some of the points that I'm making or trying to make. So the first sort of lots of questions are from the paper 2 that you're supposed to have done for today, and I did ask you to do it by today because I was going to use some of the questions as examples, really because they were fresh in your mind, or more likely to be fresh in your mind. I'm not answering the questions, incidentally. I'm just merely like trying to point out things that you could do that might help you when it comes to answering questions. So let me just say something else before I start with a proper example. And that's this thing about highlighting and underlining. I see lots of students highlight a lot, and I see them underline a lot. So they'll do something like this, and they might even do that, right? So, and I think, what's the point? I mean, what seriously, what has that achieved? Because often what happens is they underline something or highlight something and then just ignore it when they answer the question. And if you think of it, there's nothing here that's differentiated. I've highlighted nearly every single word, and you know, and there's nothing here that's going to really help me answer this question. So, you know, maybe a very judicious highlighting can be helpful, maybe, but surely it would be. I think there are better things. Now, you're having to compare in this example 3-aminopentane and ammonia, and one of the things here, and you know, there's no getting around that. You've still got to have, you know, the knowledge, right? You've still got to have knowledge. You've got to recognize what we mean by base. So you've got to think of a proton acceptor, and in both of these examples, we have got, you know, we're talking about something with nitrogen. You know, there's no getting around that you need to recognize this nitrogen, and you have to recognize the fact that it's about, you know, the thing that makes that nitrogen now gives it its basic qualities is the fact that it can accept a proton, and that's because of the lone pair. Is it all of these, any of these molecules in organic chemistry which have nitrogen, it's all about the lone pair, right? You've got to have that lone pair. And you think about the fact that it's got 3 bonds. So, you know, with ammonia, I would just draw the display formulae. And then for the aminopentane, you know, you can do it. It doesn't matter, but you can do it. This is where skeletal formulae, I think, comes in very useful. I would argue that skeletal formulae is going to be, or has the potential to be, super, super useful in respect to annotating your exam paper. And that's why, you know, it's worth spending a bit of effort getting good at it. So you get your 3 amino, okay, and then you've got that. And then the next thing, you know, I'm not saying, you know, maybe you feel this is all just too much faff, but I'm just giving you examples. The next thing is to draw my arrow. You know that I draw these arrows. And it's just then, okay, I understand what I've got to do here. This is about the lone pair. This is the thing that makes something a base. It's a proton acceptor. I look at the nitrogen. What's the difference around the nitrogen? In ammonia, I've got 3 hydrogens. In aminopentane, 3-aminopentane, I've got 2 hydrogens and an alkyl group. The alkyl group, if you get into the habit of drawing things like the arrows, for example, when you're doing anything where it's about things attached, you can think alkyl groups attached to things. It's about the inductive effect. You know, you've just begun to think, now I just need to talk about, you just need to talk about this. I'm not saying that suddenly magically makes this answer easy or whatever, but these are the types of things, all right? You don't have to have done it for this question, but these are the types of things that you could do. These are the types of your thinking on paper. And now, when you're writing your answer, here, you are looking at what it is that you are comparing. So you are probably going to find it easier to explain, because you're not having to keep in your head what is the difference between these two things. Okay. I'm just going to move through these. All right. So this is a rate equation thing. So, you know, when you read a statement like it was second order with respect to R, then I think when you see that, you should write what it's going to look like in an equation. I think you should write that R squared. And then when you see it's second order with respect to S, I think you should write that. Okay. And then, you know, you've now got a chance. You've already just done a little bit of the heavy lifting before you start to think about answering this question and thinking about putting together the equation. So rate equals K, and then you've got your, then you've got your expression, and you've already sort of thought about it. You're not going back and doing it. I mean, I'm not saying you had to have done this. And then it's a question of rearranging. And so you should be rearranging before you do anything else. And then when I said about using your calculator, and I said about using the fraction button, what you want to be able to do is to be able to write it exactly like that with the numbers in it in your calculator. All right, that's the sort of thing that I think you're looking at. Again, I'm not saying this is a big deal. In the examples that I'm showing you, I think some are going to be more effective or stronger, but it's just, I'm just trying to illustrate the types of things maybe that you could do. You know that I do the annotated versions of both homeworks and all of those exam papers that are in your shared folder. When you look at that and I annotate stuff on them, yes, some of it is to try and really explain things to you, but some of it is actually what would have helped to answer the question in the moment, right? By by unburdening some of our thinking and putting it on the paper. This one, thinking about this question at the top, compounds A and B both have molecular formula C4H8Br2. And then we read it has a singlet and a triplet and a quartet. So one of the things that I would do here is I would make a note that it was 3 environments. Okay, just that's what that's told me. If it says it's a singlet, a triplet, and a quartet. The other thing I would do is the moment I see this triplet quartet, I should be thinking CH3, CH2. That would take up, so I'm not trying to solve it from the whole thing in one go. I'm just trying to chunk it, break it down. That would be 5. That's 5 hydrogens, right? So if I've got 5 hydrogens and I look at how many I started with, I've got 3 left and I have a singlet. So to me, that says I've got a CH3. Now I appreciate some of this is about, also being stronger and more confident at NMR. I've now used everything in this formula except a carbon and 2 bromines. I have got my triplet quartet, providing I don't have any hydrogens here. And you know what? I can make that work, no problem. So there might be a bit more trial and error to it than that when you're doing it, but you're just trying to think about it. And then, okay, the 3 environments is more of a confirmation at the end. When I look at it and I think, how many environments, hydrogen environments have I got? I've got 1, 2, 3. So it's like a way of checking at the end. So does this fit and suit what I've done? Yes, it does. But I didn't try and just do the whole thing from scratch. I took a part of it and thought, right, well, that's got to be that. And then I just tried to build from there. And okay, you might not have got there as quickly. You might have struggled a little bit, but to have that bit already probably would have made that bit more likely to happen. And it's about also, the time that you're spending on it. I mean, bear in mind as well that, you are months from what would be or would have been the real exam. So this is not about, you can't be perfect now. You can't be brilliant now, but you have to be striving and working towards that. When I'm looking at this one at the bottom, compounds C and D both have the molecular formula. And it is important to read the information carefully. And again, I know that's sounds like obvious, but I think sometimes students, you can skim read stuff. When we look at this, when you look at that, you've got 6 carbons and 6 other atoms. And I think what you've got to see is that's benzene-like. So the fact that you don't actually have many other atoms besides carbon, you've basically got 6 atoms and carbon. That's benzene, basically, okay? When you look at these statements, you know that benzene has 6, right? And we're talking about carbon NMR. So in theory, the maximum number of peaks we could have in theory is 6, okay? Now we've got 2 and we've got 4. And that says to me symmetry, okay? The moment it's fewer, in most cases anyway, the moment it's fewer than what the maximum would be, then that's suggesting symmetry. So the fact that I've already thought it's benzene means that I can just go ahead and draw the benzene structure. And then I've got to think about how I stick the bromines on. I've got to do 2 of them. Okay, so I can go ahead and I've already drawn that structure. Now, my concentration, my thinking is about how can I stick on 3 bromines so that I end up, because those are the bits I'm going to show. How can I stick on 3 bromines so that I end up with lots of symmetry for C and some symmetry for D. Okay, and there might be a little bit of trial and error, but that's fine because you've basically chunked it along, and now you're just trying to do that final piece. So obviously you're going to put in a bromine anywhere, so why wouldn't you just put it in the center like that? And it needs 2 peaks. That means there's got to be lots and lots of symmetry. Okay, now that means really there are only 2 types of carbons. So there's going to be a carbon with the bromine, and there's going to be a carbon without a bromine, right? Those are basically going to be the 2 types of carbons. So if you think about how you could arrange this, and you might not get this straight away first time, but you check in afterwards, you start to think about it like that. And basically what you've got is all of those are the same, and then all of those are the same. So you've got your 2 peaks, right? But we tried to think about it in steps, in chunks. I appreciate some of this is about awareness, but those are the things that you can get your head around between now and any sort of further assessment or final assessment or whatever. The next one, it's got to obviously be different to this. It's going to have less symmetry. I'm going to put 1 bromine down. Okay, I'm going to do that. And then I've got to think, well, look, I had a space between each one last time, so why don't I put them all close together? So there might be a little bit of conjecture. You might have to draw it and then decide. So if I look at that, I've got 1 because it's next to 2 carbons with bromines. I've got 1 because it's next to 1 carbon with bromine and 1 carbon with hydrogen. And then I've got these, and then I've got this. So I've got 4, right? I've got 4. Okay, I've just gone ahead and done that. You might have had to add it, but, it's just, I got myself into a place where I was thinking, I know it's benzene, I've got to put bromine on it. Again, I'm not saying, oh yeah, you could easily do that now, but those are the types of things. I'm just trying to illustrate the types of things that you can do. And I'm not saying that even what I'm doing is perfect. That's one of the reasons why I want to do a more formal video, because I want to think even more about it, and I want to find the best examples I possibly can, which I needed to do this in a sense to help me with that. Again, it might not be any need for you to do this. You might be able to just answer this sort of question very easily, but it's more about when you think, oh gosh, I'm having to think quite hard. If you can just go ahead, there would be the infrared spectra below. If you can just go ahead and answer it, fine. But this is a thing to help you, if you're maybe, oh, I've got to think about this. So, one of the things that you could do is you could think, well, which parts of these would be on any spectra, and then to write the actual values. And I am trying to remember the values here. So apologies if I get any of these wrong. So, we're just trying to think, what would there be? How many peaks would there be? What would their range be? Again, you might feel this is taking too long, but it's just the type of thing that you can do. And then when you're looking at your spectra, you can match it much more quickly. All right. And to be honest, if you've done 2 really well, then the third must be the one that's left behind, right? So, maybe you only have to do 2 of these, possibly. Okay. But anyway, the type of thing that you can do, So this is a thing that I think you would definitely benefit from. So this is a 6-mark question. There'll be some other 6-mark questions. Again, what sometimes happens is people, will just like highlight stuff, underline stuff, and you think, well, what is the point of that? I mean, what has that actually achieved? It's achieved nothing. And they've somehow convinced themselves that highlighting works, but then they've never really looked at the evidence at whether it actually has. The way that you could approach this, something like this, is, and this will apply to some other questions later, this is actually 3 questions. It may be 6 marks. You might look at it and your heart sinks and you go, oh my God, it's a 6-mark question. It's not, it's 3 2-mark questions. You can separate these up. You can break, where possible, you can try and break your questions down, and don't simply underline them. Don't simply highlight them. give them a number. Say that's the first part of the question, that's the second part of the question, that's the third part of the question. And then when you come to write your answers, write your numbers, and then you write your answer. And you are looking really at 2 marks, you know, because it's split into 3. You're looking to write what you think is 2 marks worth of information. When it comes to question 2, you can write that. And then at the end, you've got a quick way of checking, have I actually written enough, or have I written about the things I need to write about to get 6 marks? Because again, you know, there's been questions. If you remember the aromatics test, the first question was about benzene, and it said something like, it was a comparison with cyclohexatriene, and you had to explain the difference using, what was it, bonding and structure, was it something else as well, and data or something like that. And anyway, the point is you could have numbered each of those bits, and some of you failed to say something about one of them, one of those little things it mentioned, and not necessarily because you didn't know it, but because by the time you got to it, you'd forgotten about it. And that's where if you put a 1, a 2, and a 3 or something like that, you can be much more clearly saying to yourself, I've answered that, I've answered that, I've answered that. Okay, so you're going to see this happen a couple of times. I really think that is a very valuable thing. Okay, I mean, obviously some of these things depend on the question, but you know, you've got like lots of structures there, and you're thinking, oh my goodness gracious me, I've got like all of these complicated compounds. What you should be thinking about is, if you're going to be asked about any of these steps, step 1, step 2, step 3, what those questions are asking you about is about how it's changing. So you need to think, what is changing? All right. So what I would do is I would draw this hydrogen here, and I would be thinking in step 1, what is changing is that. That's what's changed. I've gone from a hydrogen to an NO2. In step 3, what has changed? That. I've gone from an NO2 to an NH2. In step 4, what has changed? I've gone from NH2 to HN, and then I've got this acyl group. And then when you're answering your questions, what you hopefully come to realize is that, you know, by and large, it does matter here about the benzene ring, but by and large, that's no longer relevant. You just need to focus on what is it that's actually changing. How can you explain that change? Anyway, suggestion there. You don't have to get distracted by these type names. You don't have to get distracted by any of that stuff. What's happening in step 1? Hydrogen is being replaced by NO2. What's happening in step 2? NO2 is becoming NH2. What is happening in step 3? NH2 is becoming an amide. An amine is becoming an amide, right? You could, you know, depending on what the question is asking, if you suddenly get asked about step 3, write the functional group or something, right? Anyway, again, you know, I'm not saying this is magic. I'm not saying this suddenly means you can answer the questions. It's about, can we make the question easier, right? That's what we're trying to do. Whenever you're reading a question, and again, this is maybe not the best example, all right? But whenever you're reading a question and you see a unit given that is not the conventional unit that you use in chemistry, then rather than wait until the calculation, why don't, as you write it, you know that, well, I'm telling you now, if you didn't realize this, every number they ever give you in any exam question ever, you are going to use. If you find you answer a question and which gave you values and you have not used one of the values, you have definitely made a mistake. What that means when you're reading a question like this one is, if they give you a number that is not in the unit you typically use, then at that point in time, why not write the correct value? Why not write it? Don't they give you Ka in acid sometimes when you don't need it? You'll have to find maybe that's possible, Josh, but I'd like to find an example. Okay, so let's try and find an example of that. Okay. Yeah, you typically, the one thing to bear in mind, and this might be relevant to the point you're making here, is, and I don't have an example, and I won't put one in the video. you often get text at the beginning of a question. Like, let's say it's question 2. You'll get text at the beginning of the question, but that text is before, say, the actual first part of the question. So part A, and so anything that they say in that information before part A, or question A, or question, could be relevant to any of the questions that follow. So where a lot of students get caught out is they get given a piece of information right at the very beginning, and then it gets to part F and it asks them a question, and basically you needed to look back to the very beginning. So if that's going to happen, Josh, it should be clear if you understand that that value that you're being given is separate, is before the sort of question that you're then answering, if that makes sense. Okay. All right. Anyway, do the conversion straight away as you read it. You're going to have to do it anyway, so why not do it then, and then you can just focus on answering the question as you would normally answer it. Oh, this is a nice one. Okay. So how could we go about making this easier? How can we chunk it down? Okay. They tell us it's a dicarboxylic acid. So that means it must have, as part of its structure, it must have that. Okay. Now, if we add all of that up, it is 2 times carbons, so 2 times 12. It is 4 times oxygen, so 4 times 16, and 2 times hydrogen, which is 2 times 1, and that equals 24, 64, so that's 88, that's 90. Okay, so when we look at then trying to work out what's in the middle, that question mark, the question mark equals 118 minus 90. And you think about that, and it's going to be carbons are involved. So we're going to get to 28. So do you know what? I'm going to go with 2 carbons. So that's going to give me 24. So I'm then lacking 4. We know that we normally have hydrogens. What would they actually be in the middle? Well, they would be CH2. But again, what I've tried to do is, I've thought, if I'm given that information, then I definitely know this. And what does that add up to? And then what's the difference between what I know has to be there and what I'm still trying to work out? The difference is 28. How can I make 28 work? Okay, type of thing. Again, it's practice. It's thinking about, it's being able to recognize those things that you can do. That's why you need to practice it. But that's actually genuinely how I would have approached that question, right? It's not just me trying to give you an example. I would genuinely have approached that question that way. Okay, what do we got here? All right, so we've got a bit more of a calculation question. So there's a couple of things I want to mention here. So there's going to be a few things I'm going to annotate. And the thing is, the more that you are doing practice questions, generally speaking, the more that you're being exposed to questions, the more that when you're doing them and you look at your answers afterwards and you compare them with the mock screen, the more that you will begin to see things, repeated things. But just because you see them repeated doesn't mean when you come to do the calculation yourself that you will remember that. So, but what you might do is remember it while you're reading the question. I'll try and make that clear. So, reading this question, student dissolved some of the dicarboxylic acid from the previous part in water and made up the solution to 250 centimeters cubed in a volumetric flask. In a titration, a 25 centimeter cubed sample. Now, the moment you see that 250 to 25, what I would do, because you're going to need to remember this, and you will realize this the more you practice you do, but if you write it here, you are probably less likely to forget. That's times 10. At some point, you are going to have to do it times 10. People forget that, right? So that's one thing to say that we could do here. The other thing is, and this is going to be a more general point for other questions as well, if you are given a volume and a concentration, even if you have no clue what to do to answer the question completely, that is the first thing you should do, is work out moles. If you are given a volume and a concentration, you should work out moles. What that means is, in any of these titration questions, in any of the acid-base questions that you get, there is literally no excuse for getting 0. Literally no excuse for getting 0, because they will always give you volume, concentration. So at the very least, you work out moles, and that will be 1, possibly, depending on the question, possibly more than 1 mark. So at least you've got something. Okay. And then if we think about the rest of the question, the other thing I would say is, obviously that's the thing you're concentrating. That's the bulk of the question, is calculating the mass. The second thing is, if you write your numbers 1 and 2, maybe by writing that 2, maybe you are less likely, because a lot of you do forget, maybe you are less likely to forget to give the appropriate number of significant figures. There is something else about this that you could be adding to help remind you, and that is, because that's the thing that people will miss. So, you know, when you've just done a question where you've had to work out the structure of a dicarboxylic acid. So you do have this dicarboxylic acid in your head. Even if you didn't get the correct answer, you've still been thinking about these 2 carboxylic acid groups. I think, therefore, you've got to think about that. In fact, sorry, let's redo that. Sorry, this is not perfect. Okay, but anyway, little things like that, maybe you could think about on the way. Maybe you forget about that. I'm just trying to illustrate the types of things. So there was quite a lot here on this example question. Just reminding ourselves, dicarboxylic acid means 2H+, because this is neutralization. With neutralization, always think about how many hydrogen ions, how many hydroxide ions. Always think about that. This, absolutely, lots of people forget about that when it comes to it's not like they didn't see it, they just forget in the flow when they're in the midst of the calculation. So why not remind yourself, put the times 10. Always do that calculation, even if you have no clue what else to do. Once you've done that, you might have a better idea of what to do next. And another example here is, okay, that's the bulk of the question, but there will be 1 mark here. Lots of people will forget that mark. So if you put your 1 and your 2, maybe you're less likely to forget it. Okay, this is a really tiny thing that I'm going to show. Again, you might feel it's a bit pointless, but hey, it's just another example. So we've got to work out the ester that's being formed here. And you might have no problem with that. But one of the things I would say is, if you've got something which has got either this group or an amide group and it's reacting, then why not just draw where it's going to break? If you just draw where the bond will break on the picture, like on the page, then what you're looking at is, you're really looking at this joining with this. And then I think, you probably would have got it anyway, sure. But I think just even doing little things like drawing where the bond breaks just makes your life that little bit easier. And to be honest, actually, if you are remembering to do something like that because you've thought about it in your practicing, then you're probably going to remember all sorts of other useful things to do with ester groups. Okay. Anyway, that's just a tiny example. What we got here. All right, this is quite nice for some examples. So when you're reading this question, student carried out an experiment to determine the enthalpy of combustion of ethanol, combustion of 457 milligrams. The moment you see that milligrams, you should be thinking, right, got to turn that into grams. Okay. Then they give us the temperature of the water. Then they give us the temperature rise. So you don't have to. No, it's not. I've exhausted the ones from that paper, right? I've just picked some other ones. I've picked some paper 1 questions, not necessarily the 2019 paper 1, just paper 1. You could write that change there. I wouldn't really worry about it, because you can easily do that when it's ready. But very important, because this is something that people miss. You don't have to write temp rise. I'm just writing it here. Temp rise equals exothermic. Because I tell you what, a number of people will forget the minus sign at the end. So they go through the whole process of the calculation. They get to the end, and the calculation does not give you the sign at the end, right? It does not give you the sign. You have to remember to include it. You have to make a judgment. The thing then that I'm saying that you could do whilst you were reading a question like this, because you're just thinking about that part at that moment and not thinking about, doing a whole massive calculation, is fundamentally that, to make a note of that. And, you could, when you're coming now to numbering it, it says calculate a value in kilojoules per mole. You could think of it, just a suggestion, you could think of it like that. And if you have numbered this, then it's going to make you ensure that you don't forget it. But I promise you, there will people who miss that every time. And that can actually be more than 1 mark lost, actually. So there we go. There's another example. Okay. You don't get many equations in chemistry. You certainly don't get many graphs. The graphs that you get are, well, the ones to do with thermodynamics and this, sorry, the Arrhenius equation, activation energy. They can throw people, they've given you the equation, but you know what? If you can remember that this is the case, I think writing underneath that is useful. And so if you do have a highlighter pen, you just think about, it's just going to make that connection, just make it a bit more secure, make it stronger. All you've done is written this. This is quite generic. This is something that you should remember is a way of viewing an equation like this. It just makes then the equation easier. This is why this is ln k is your y-axis. This is why 1/t is your x-axis. And if you've just written y equals mx plus c and you've written it in the right way underneath, you've just unburdened yourself. Now, obviously, you needed to know that piece of knowledge, but if you do know it and you write that, you've just made, I think, less likely to make a mistake. That's all, okay? Because you're less likely, you're going to remember that gradient now equals minus EA over R. So anyway, it's a tiny thing, but the sort of thing that might help you answer this question or might make it easier. Right. So here's our time of flight. So interesting. So we could read through this question, gives us all various information. But fundamentally, actually, where we need to start is to know what is it we're trying to work out. And ultimately, it's the distance, okay? Or it's the length, but it's classed as distance. And we can remember about the significant figures. Now, curiously and unusually, they've only given us the kinetic energy equation. They always give us that, but they haven't given us the other one. So you can see there's no length in that. There's no distance. They have given us the units to speed or for velocity. You might just remember this anyway, or the units can help you because velocity is meters distance over time. But anyway, we include that. We write that. And now it's a question of I've got to work out what D is, right? That's what that's asking me to do. So let's just focus. Let's just forget the numbers for the moment. Let's just put all of my mental energy into getting the equation ready. So, you start with your kinetic energy equals half mv squared. Okay, now you're going to replace V with d over t. So you can take it as easy as you wish in terms of you can just put brackets. So you've got d over t, if that's what you want to do, squared. And then we can make that, it doesn't matter that you're really spelling things out very carefully. Now we need d on its own. So whoops. So now you need to, now you need to be able to rearrange the equation, right? So this is the thing where if you feel like this is something you struggle at, you've got to practice at. But we end up with kinetic energy times t squared, or 2 times that, sorry, because I've times both sides by a half, both sides by t squared, divided both sides by m equals d squared. And then I just need to remember to square root the whole lot. So, this is not shortcutty really, is it? Other than the fact is I'm just trying to illustrate the point that you are trying to just be systematic about it. And then when you write now you can start looking at the numbers. Now you can get all of the numbers ready. That would be the next stage, getting all the values ready. And then once you've got the numbers, you've got this equation all good. You can take t out. If you're feeling comfortable with the maths, you can take the t out, whatever, it doesn't matter. But now when you write in your calculator, you need to write it in your calculator like that with the numbers. And if you're not sure how to do that, that's something we can look at together. Okay, but then, what we've done also is we've numbered, all right? We've written the equation. Anyway, again, just a little example. Okay, so this one here, so use your knowledge of structure and bonding to explain why sodium bromide has a melting point that is higher than sodium and higher than that of sodium iodide. So I would rephrase this question, I would show this question visually. So you know that sodium bromide has a higher melting point than sodium. And you know that sodium bromide has a higher melting point than sodium iodide. So this is basically question 1, and this is question 2. So you've now broken it down into 2 3-mark questions, likely anyway. The next thing I do, they say structure and bonding. So what bonding is there? Ionic and metallic. So you are just making a comparison. Okay. And then with the other one, they're both ionic. So that's not a difference. So what is different about them? There's only one thing that's different about them. Now you still have to work out why that makes a difference. But, now you've got an approach to your question. You're thinking, all right, I'm going to just start with comparing those. That's my first part. I've broken it down. I only need to occupy my brain on that for the moment. I've just very quickly jotted down the types of bonding. So now I've just got to make a comparison with them, about them. And fundamentally, this greater than tells you which is stronger. So all you have to say is explain what that is, and have that one stronger, right? Because they've told you it's stronger, because a melting point is basically a measure of strength. On the other one, okay, you've got to think about what the difference is here. So there is still, there's knowledge and awareness, but you have to talk about the size of the ions and how that affects the electrostatic attraction. Okay. Anyway, we've still tried to what looked like a big 6-mark, lots of line questions. We've broken it down into parts. We've thought about them separately. We've only had to use our brain and one bit at a time. Okie dokie. All right. So for a question like this, and again, I am slightly taking them out of context. So, there will be other circumstances, but it's telling us that it reduces whatever this species is. It reduces vanadium. Okay. So what we could say to ourselves, if this is going to be useful, it's oxidized. If the other thing is reduced, this species is oxidized. Next thing I would do is, and I would do this probably every time I get one of these tables, because it doesn't take 5 seconds. I would just draw these arrows on there. Okay, I would do that because reduction is the gain of electrons. Well, you've gained electrons going that way, and oxidation is the loss of electrons. Well, you've lost electrons going that way. So if the thing is oxidized, that means it's got to be going from right to left. That means already we are looking at this side. Okay, so we are going to be choosing something from this side. All right. And then the other thing, and again, you've got to remember this, but it's in my notes. Positive. So positive is oxidizing. Negative is reducing. So we're looking at the most negative one, and we've said it has to be on the right-hand side. So it's zinc.
Wouldn't it be iron 2+? Because you have to do it to no further. And then wouldn't the zinc 2+?
Oh, you're right. Sorry, you're right. I haven't read the question properly, have I? You're right. Sorry. Apologies. Yeah, you're quite right. Sorry. So where are we? It's got to go to V2 plus and no further. Yeah, it would. Yeah, okay, that's a bad example. I need to edit that out of the video. Let's move swiftly on. For the purposes of anybody watching this video in the future, please ignore everything I've said on this particular slide.
Can you explain why the iron wouldn't let it go further, but the zinc would, or do you not want to do that?
I tell you what, it's really actually annoying thinking about it that they've not done it in order. So it's unusual, isn't it? What are we doing? So the way to look at this, okay, this is a side note, isn't it? This is where those fraction things can come in useful. So if you think about this, so you put the left-hand side over the right-hand side. That is greater than so you do it. What you're doing here, what we're doing here is we're going, step by step. Okay. So this isn't how this would be too long-winded for your answer, for you writing an answer. But if it's greater than, then you're going to get this happen. Okay. Then so that would be fine. So iron would get it down to VO2 plus. Now, what if we used zinc, right? So let's just compare zinc. Now, zinc is also going to get us down to VO2 plus. But if we then look at the next one, which is VO2 plus over V3 plus, that is greater than zinc. It's more positive. That greater than means more positive than, right? So it would continue to be reduced. If you looked at chlorine, for example, if you just want to say that's the most positive one, so the chlorine is, so you're putting the left-hand species over the right-hand species. That's what you do. The greater than just means it's more positive. You can see that plus 1.36 is more positive than plus 1. So then we write the other species. And so if in any reaction like this, I've got to move it along a second, you can see it wouldn't reduce, because the way it would go is it would go like that, and that is not reducing the VO2 plus. So yeah, does that make sense ish?
Yeah, it does.
Okay. Yeah. Okay. That was a really bad example generally for what I'm trying to show. I'll try and find a better example for electric.
Yeah. It does.
Okay. Yeah. Okay. That was a really bad example generally for what I'm trying to show. I'll try and find a better example for electrochemistry for when I show it. So apologies for that. Well spotted. Thank you. All right. So this is something I do every single time I ever in with you, and you know it's been a long time we've been together now. Every single time that we have ever named an organic compound, and I have named it with you, every single time I have done the numbers. I've written the numbers on there. And you lot, half the time, well, I never see you lot do it. And the thing is, okay, you get it right, but sometimes you don't. So one of the things I would suggest here is when you've got branching at the end of something like this, just rub out the number and put the branch on there. And then just put your numbers down. So, you know, now we can see much more clearly it's pent. I know you got this right, a lot of you, so it's not about this particular question. It's just the principle. We can see we've got 2 amino, 4 methyl, pentane dioic acid. All right, sorry, pentanoic acid, sorry, pentanoic acid. So, you know, the other thing is that you could try and just remember, and because you could do this whenever it's about naming things, naturally occurring amino acids are always 2 amino. All right, they're always 2 amino. Anyway, but it's about that numbering. How many times have I numbered stuff and you lot never do, and then sometimes you make mistakes. So just taking some of the load off my brain, aren't I? Question like this was in a homework recently. I mean, a lot of you got it right, but I'm just using it as an example. But what I see is I see people do this and they go, brilliant, but then they don't draw an ester. So for something like this, maybe the thing to do is you're supposed to be drawing a structure with an ester. To actually remind you about that properly, why don't you do something like that? And then when you write your answer, you can be going, have I actually got that in my answer? Instead of just underlining ester, draw what it's going to look like. Again, just a tiny suggestion, right? Just a tiny suggestion. And it's about examples of things. Right. This was a question you also had in a piece of homework recently. So there's a few things we can write here. So one of the things I would do, this is about neutralization. So one of the things I would do, especially when you've got acids and alkalis, is to write how many ions they would produce, all right, for their formula, because people do get caught out by diprotic acids and so on. And you know, if you did your formula of barium hydroxide, then you're less likely to forget it's 2 hydroxide ions. So a lot of you realized, but you know, some of you didn't. So, you know, and again, it's you know, if you've got to be able to know that, haven't you? So there is an element of, you've got to have the knowledge, certain knowledge, but this is where, you know, this is foundation. When I say foundation, I don't mean it in the sense of being easy. I mean it is in terms of being fundamental, right? Being able to just think what barium hydroxide's formula is going to be. The other thing you could do as well is you could write, when it's got, the moment you're given Kw, you're going to be using it. So you could write the expression here. So again, you're just getting it ready for when you need it. And you're being asked for a pH. So the other thing you could do at this point, or you could just leave it, but it doesn't matter, is you could get it so that you've got it in the form for when you need to put the numbers in. Again, it's not the end of the world if you don't, but it's just the type of thing that you could do, right? So you just worked it through, just getting everything ready for yourself. There is no excuse for getting 0 marks on this question at all, because at the very least, you should be realizing, because I keep telling you now, every single time you get a volume and concentration, you should be doing that calculation. I can't quite remember now. If you'd done both of these, I think it would have been 2 marks. And then I think a third mark would have been, but it might be that it was 1 mark for those 2, but the third mark would have been then doubling the barium hydroxide concentration to get the hydroxide concentration. But anyway, it doesn't matter. There is no excuse for getting 0, because you can absolutely do those calculations. Okie dokie. Right. Here we go. Oh, 7 marks. Woo! So you don't get a lot of space. So, you know, I am zooming in, but I think with a pencil you can do this. But, you know, maybe you need to rewrite it. Anyway, this is where you want your ice. If you try and do this without this, you are stuffed. So, you know, this is a strategy, right? This is exam technique. Your initial change equilibrium, that is a strategy. It's reducing the load. It's giving you a structure. It's giving you a table to fill in. So you look at the information and you start with that. And then the other piece of information they give you is the yield of methanol. So what I've written so far, I haven't had to do any thinking about. That is literally the information they've given me. Then I can start filling the table in. See, the table just means that you're just focusing on one thing at a time. So you can just focus on that one thing at a time. Whoops. You've got to be a little bit careful. There's little mistakes you can make. Remember, you've got to look at the molar ratios. All right. So it is a 1-to-1 with carbon dioxide and methanol. So it's a minus 0.86. So that's 0.14. So, you know, there are places you could slip up on. And that next one is, what is that? Is that minus 2.58? Where's my calculator gone? Hold on. So here we got 3 hydrogens to every 1 methanol. So it's 0.86 times 3. So minus 2.58. So 0.42. Okay, and then the other thing you could do at this point is add them all up together. Because that, you're going to be doing your mole fractions next. So that's total moles, isn't it? For when you've got your mole fractions. So now you're able to just be much more systematic about mole fractions and then the rest of it, etc., etc. Thinking about, you shouldn't have used blue. It does, to be fair, it does give you space. It makes it obvious where you're doing these things, but just in case they didn't, those are your 3. They will actually give you a line that is clearly KP, and they'll give you to put your answer, and they'll give you a line that clearly is for units. So they are reminding you about units, but I think if you do this, it's better for that. It's better for remembering about significant figures. But you know, you might not have quite enough space. I don't know, but that's the type of thing you should be doing for something like this. All right. This is not something you've fully covered yet, so I don't want to. I just want to make a general point here. It's 6 marks. It gives you a volume and concentration. It then gives you a volume of gas and temperature and pressure, and then it's asking you to use this information to calculate the oxidation state of the vanadium after the reduction. Now, I'll tell you is this bit is hard, and you haven't actually done it yet, so it'll be especially hard, right? But that bit's hard. But that's not hard. And providing you know, I mean, and in the grand scheme of things, that's not hard either. So if you just did those 2 bits, if you just did your concentration volume and you did your PV equals nRT, I can't remember exactly how many of the marks it would be. It's either 3 or 4. So it's a 6-mark question that you would class as a hard question, but 3/4 marks are not hard. Thinking about when you're reading it, you know, you've got to remember that PV equals nRT is not in centimeters cubed. If you want your quick shortcut for turning that into meters cubed, you just write the number exactly as it is in centimeters and put 10 to the minus 6 after it. Okay, that's your conversion. You need to remember that is, but you can be writing on it, yeah? You can be writing on it as you're looking at it, getting each bit prepared, each bit ready, because you know degrees Celsius is not what you use. You know that centimeters cubed is not what you use. Now, you do those 2 calculations, and I think it's 4 marks. It could be 3, but I think it's 4. That might be really hard. That is not really hard. So don't let this stop you from getting these marks here. Think about it, break it down. That's question 1. That's question 2. And then this is question 3. you can do 1 and 2, no problem. Right, but if you put those numbers, you're helping yourself chunk it into bits, into parts. Okay. Do I want to do that? Oh yes, I will do this one. Or we'll talk about it a little bit. So you're going to have to do an ICE. This is actually an interesting question. What I would say is, when it's a titration, you basically are working backwards, sort of. So they give you the initial. So they give you ethanoic acid. Where is that? There it is. They give you ethanol. So again, you're just setting up, just filling in your table. One of the things, then they don't give you anything else here. It's this part. This is the thing that gives you that will give you your equilibrium of ethanoic acid. So yeah, there's a little bit more tricky, right? So the concentration, sorry, the moles of ethanoic acid will be based on this. So one of the things you could just write is ethanoic acid is H plus, sodium hydroxide is OH minus. So you've got a 1-to-1 ratio. The other thing you could annotate onto this as you were reading it through, I appreciate I haven't done this as systematically as I could have done, is notice you've made it up to 250. You've got a 10 centimeter sample that you're titrating. So you've got to do it times 25. Just little things to remind yourself. So in a sense, what's happening here is this is going to give you this, which you then need to times by 25. And you end up with that. And then you've got to fill in the rest. But anyway, generally speaking, I mean, yeah, you might not have written all those arrows, but the things I think you could have thought about are those things when you're beginning to answer the question. I appreciate I'm going quite quickly, but you can always pause and look at this afterwards. Okay. A sample of ethane dioic acid, this is a nice question, was treated with an excess of an unknown alcohol in the presence of a strong acid catalyst. The products of the reaction were separated and analyzed in a time of flight, and 2 peaks were observed. Okay, so what's happening is we could write our ethane dioic acid because we should draw the structure because I think it's going to help us. You could write the structural formula, it doesn't matter. It's reacting with an alcohol. We don't know what it is, but we know it's an alcohol. So the R is the rest of it. We know that it's going to be water that's produced, and we know, well, that's what we're now thinking about. Okay, what's going here? So the first thing to do would be to think, well, what is the mass of that? And actually, it's just like the one we did earlier. It's 2 carbons, 4 oxygens, 2 hydrogens. If you remember earlier, that was 90. So if we add, why are we getting 2 peaks? Well, okay, this is the tricky bit. That's because we could have 1 ester, or we could have a diester. So let's just focus on the most simple one, right? The most simple one would be the most obvious, if you like, rather than simple, would be that our product was HOCO. That would be our most simple product, wouldn't it? Now we know, or we can work out, we can think, and this is where maybe I've over elaborated the chunking, but anyway, we know that now is 89. So 89 plus R, and that's going to be the simplest one, isn't it? That's going to be the smallest one. It's only one alcohol we're adding. That equals 104. That means R equals 15. And 15, you probably, hopefully won't have to think very long about it, is CH3. So why have we got, what's the difference between 104 and 118? That's a difference of 14. That is the equivalent of replacing the other hydrogen on the other carboxylic acid with our CH3 again. So what were we actually supposed to identify the species responsible for the 2 peaks? So it's going to be, I'm not going to draw the whole thing, but these are our 2 species, but I'm just writing R. But we've worked out from the first one what R has got to be. Now, the way we've tried to make it easier for ourselves is we know we've got to have this part, so why don't we use that number and think, what is the difference between them? What is the difference between that and one of the peaks? It's 15, and that has got to have come from the alcohol. It may have helped you to have written this equation. I don't know. Again, I'm not saying you would definitely know to do exactly that, but it's thinking about the types of things that you can do. How much more have we got? Oh, right, do a little bit more. So NMR, right? This is the only question in your specification. We've done this before, but this is the only question in your specification where it's been a long question. And this was in a sample paper. In fact, this was in the very first sample paper. So in the very first set of sample materials, which by and large they have developed from, because they've realized some questions were probably either too hard or too long in terms of how long they took to write. So in the first set of sample questions, they had, for example, a activation energy graph question, and you had to do both scales. So you had to write, draw, determine both scales. That takes too long for an actual exam, a real exam. So when they actually had an activation energy question, graph question in a real exam, they did the more difficult scale for you. So whether they would ever do quite something like this, I don't know. But when we approached it together, what we did is we did it by annotating the spectra. You know, let's forget the whole lines, 8 marks of lines. Let's just focus on the spectra. Let's just focus on writing things that we know or can work out. So the first thing we do is we look at what's the highest common factor. It's 0.4. Divide everything through by 0.4. 4, 1, 3, 6. Let's add those together. What's 1 plus 4 plus 3 plus 6? It equals 14. Let's just double check our formula at the beginning. Okay, 14 hydrogens. So there's our hydrogens. We've done that. Next thing I would do is I would write the splitting patterns. I think they would make these clearer in any one that they actually used, so that you could see. Okay. Now, the other thing is, and we would have done the earlier part of the question. So we would have done this earlier part. That there is OH. In fact, we would have written that. You know, we could have written that on our thing. That's something we could have written. And frankly, you know, that's when you start to piece it together. You start to think, okay, I've got a singlet with 1 hydrogen. That has got to be my OH.
Also,
sorry?
Isn't that a triplet?
Where?
The quartet that you put on the right. Isn't that a triplet? Oh,
yeah, sorry. Apologies. Do you know what happens is when I'm talking and writing at the same time, I'm more likely to make a mistake. It's like when I'm right on the board and I'm saying what I'm about to write. I often miss a word, or it's working memory, isn't it? Limited capacity. Anyway, right, where was I? So that's the thing. That's got to be our OH, right? I think, you know, again, there is an element of you've got to understand NMR to a certain extent. You can't, and this is not a magic for making NMR suddenly dead simple. What it is it's a way of making NMR easier. You see a singlet in 3, you've got to think that's CH3. Okay, you've got to think that. And then the triplet quartet, that again has got to start sticking, but you've got, that would normally be CH3, CH2, which would be 3 and 2, and yet we've got 6 and 4. I'm not saying that's dead easy, but you know, you've now got every single part. And the one other thing is that you could add to all of this so that you're really ready, is that there are 4 environments, because you've got 4 peaks. So what you've got to have, so if we're thinking about things in your long-term memory, right? If you're thinking about stuff that you've got to know, because it will make it easier, is you've got to know that in NMR, if you get a triplet quartet, they are 99% likely, in fact, I would say 100% an A level, going to be CH3, CH2. It's like, I would literally say it was the first thing you looked for. Is there a triplet quartet? If there is, it's CH3, CH2. Sorry? I can't hear you, Louis.
Oh, can you hear me now?
Yeah.
Yes, and then for the other ones, a singlet with 1 is always going to be an OH.
Well, given that we've established there is an alcohol, yes.
Could it be anything else? That singlet with 1.
Yeah. Sorry.
Like, what else could it be though? The singlet with 1.
It is possible. It is possible that a structure could be there where there was no hydrogens on adjacent carbons, and it was the only hydrogen. It's unlikely, but you know. The reason, let me just do this triplet quartet thing, just to maybe spell that a little bit clearer. Why is it a triplet quartet? If you look at these hydrogens, on the carbon next door, there are 3, and it's N+1. So this would be your quartet. This would be your triplet. And the fact that our quartet is further to the left, you know, whatever's here is going to be more electronegative. 4 environments, and we've got how many carbons? 6. So that equals some symmetry. That's the other thing we could say. Okay. Like I say, you know, I mean, I'm not saying there's more practice. You've got to practice these things, but I think this is a wonderful example that I've done many times with you before. A wonderful example of how writing on the paper makes it easier. How you are taking some of the heavy load off your brain by just getting it down in separate parts, and then you can piece it all together. I'm just going to do a couple of. I'm not going to do every one of these now because the time is ticking. You know, again, you might find this dead straightforward, but do you know what I would do to make this a little bit easier? And of course, it does rely on you remembering this stuff in the first place. Is you might hopefully remember this is all to do with intermolecular forces, maybe. And why don't you just write the formulae? If you write the formulae, right, you just take the first one to give you your prompt. Then you can think, well, hold on a minute, I know it's all about size. So you could just do them in order and then find the right one. So it does rely on it, but again, I'm just trying to say that if you've written something down, maybe you're less likely to pick the wrong one. You know, you've still got to know these things, but you know, here, what we could do here is we could just simply, and again, you might not need to do this. Maybe you can just do the question quite easily. We've got a carbonyl, and we've got I would write no OH. And so when you're going through them, that doesn't have a carbonyl in it. Well, that has an OH, but we don't have an OH. That does have a carbonyl in it and no OH. That does have a carbonyl, but it also has an OH. Don't know, right? You're just systematic, just trying to not keep it all in your head. What is it got? What is it not got? This one, you might see this. What would be a quicker way? I mean, you can. What you can do is you can, when you're looking at what's being reacted, you could just add them on, and then you could just, you could try and do that type of thing. It doesn't really matter, but I guess, and then decide, have you got a carbon with 4 different groups, or alternatively, maybe this is not so. Actually, this wasn't a very good one to pick, actually, was it? But it might help you work out that doesn't have 4 different groups because 2 of them are the same. I don't know. Obviously, if I've added these things here, that's just a single bond now. All right. I don't know. Maybe that's a bad example. I'm sorry about that one. Okay, this is an interesting one, and you might have to do a little bit of. You might be a little bit of trial and error, but there's still things you can do that would make your trial and error more effective. So it's got a polymer chain formed from the random polymerization. Interesting, right? Random. So one thing to do you could try is, there's going to be 2 polymers, and that because it's an alkene, this is clearly an addition polymer. There's no amide bonds. There's no ester bonds. So this is about the double bonds, and they would have been across only 2 carbons. So your monomers are only 2 carbons long, right? That's one thing you have to think about. So you could just go, okay, well, what if I draw my lines here? Do I have clearly 2 types of monomers? Well, that's the one with the CF3. Oh, and that's one with just F. Oh, and that's one with just F. So they're the same. So, hold on a minute. So let's call that A. Let's call that B. Oh, yeah, that's B. That's A. That's A. That's B. And then when you're trying to work out, it might have taken you a bit longer to do that. You might have drawn your lines in the wrong place, but I would start from the left and just do 2 along. Then when you're trying to work out the actual monomers, just put the double bonds between the carbons. All right. So anyway, again, it's just annotating and making it easier. For this one, I would do skeletal formulae. In fact, I haven't done enough skeletal formulae today. I should have picked more examples where I could do skeletal formulae. So we've got propan 1-ol. We've got 2,2-dimethyl. We've got butan 2-ol. And we've got 2-methyl. We've got butan 2-ol and 3-methyl. And then we've got pentan 3-ol. And what you're looking for is it's got to be tertiary, right? Because if you can't oxidize a tertiary, you can't reduce to make an aldehyde or a ketone. You can't reduce an aldehyde or a ketone. So that would be something you would have to have recognized. But if you've drawn your skeletal formulae, then you can spot your tertiary much more clearly, hopefully. And then you get your answer. But I think skeletal formulae is a massive, massive help. But you've got to get good at it. And where are we? Oh, right, we're at the end, aren't we? Okay, so let's stop